So yes, I'm going to talk about Markov Chain approximation to identify financial fraud. So a quick question before starting. Is there anyone here that knows Markov Chain approximation, what it is, and worked with it maybe? Maybe? Yeah, okay. Well, for the rest, don't worry. You will learn about it during the course of this talk. But you use Markov Chain in different areas, and I came across this nice tweet which says Markov chains are used widely in industry, and what I want here to point is this last sentence, that they are actually used to generate the scripts for the final season of Game of Thrones, right? And but don't worry, I'm not going to spoil the final episode here. Joking aside, now let's get serious. I'm going to talk about financial fraud. The introduction is here, the outline of the talk. There will be an introduction about financial fraud, artificial intelligence to fight financial fraud, and one of the methods, it's anomaly detection with Markov chains, which I'm going to introduce and talk about it here. An introduction to what it is, sequential data, and more like technical, how do you do some encoding strategy. And don't get worried, it's also a demo notebook which will show you how to build the Markov features from scratch. And at the end, conclusions and prospects. Okay, I'm not going to say what is machine learning. You probably know, and if not, you heard a lot of talks during the workshop. But what I want to say is that AI is widely used in different areas, and of course also in financial sector, where we use machine learning for trading strategies, for credit risk assignment, and for fraud detection. AI has shown to be a successful tool for battle the financial fraud. When you talk about financial fraud, there are different types of financial fraud, and when I was preparing this talk, I went like, okay, what about I go and make a nice summary of how many financial frauds there are, like how do we group them and so on. There was a long list, so I said, okay, I'm going to share here all the commonly known, starting with transactional fraud. I think you already know, or you can guess what is transactional fraud. I'd like to share a story here. One day a friend of mine came to me and said, hey Floriana, I just got a call from the bank. Someone duplicated my card in Indonesia. I was like, Indonesia? I said, yes, I was a few months ago in Indonesia, and someone tried to actually use it this morning. And I'm like, really? Yes, but as I already had used it last night at one of the supermarkets here, that was kind of a suspicion, activity, that how you can be at in a time difference of 3-4 hours in two different places like Netherlands and Indonesia, right? So this is an example. There we have loan fraud. I'm going to talk about this and give you an example later. So the basic idea is you apply for a loan, you get it, and then you're actually not going to pay it back. You take the money and disappear. Also, the CXO fraud, it's known. I wanted to share a story, so I found this story in the news, and it's like when you get mail, you are in charge of the transactions, and you get mail and calls by your CEO saying, make this transfer urgently, and this kind of stuff. But you can also Google this link and find more out stories about this kind of fraud. Okay. Of course, we are fighting fraud. We want to suppress fraud, and there are advanced methods that are developed to deal with this matter. So we want to identify financial fraud. We want to identify the patterns. Of course, separate them, distinguish them from legitimate clients, and also to completely suppress fraud. Now you might say, okay, so we are advancing, and why are we talking about it? Why we haven't completely suppressed fraud? Well, there are some challenges, of course, and one of the challenges, it's the imbalance that I said. So the number of legitimate clients compared to fraud clients, it's very imbalanced. We have very low fraud cases, which is very good, right? But makes our life difficult. And the one who are data scientists in the audience will actually really understand what it means to have imbalanced data sets. Another challenge is the concept drift. Fraud is evolving actually constantly with time. Seems that these fraudsters are constantly adapting their model to get around the current system of fraud detection, and somehow they manage to do so. Last but not least, and also important, we normally do not have a target. I mentioned before the example with my friend's story, and like then you would say, which is the target? We don't have a label. How would you know that this is actually a fraud? How would you label? And this is an easy example. Let's say that it happened in 2 different countries with a time difference and other things like that. But there are other things that you cannot actually, you don't have them labeled on your data set. Despite the challenges, there are also new opportunities, and one of the things that we are going to talk today, it's also the web collected data and how the client is actually interacting with the web. To be more precise, you heard about loans. Maybe you thought of getting one, or you got one when you were a student. If not, you probably know what a loan is. So usually if you have something online, like a loan calculator, you have the possibility to explore how much you can get and for how long you can pay it back. As an example, here I have generated this, I'd say, slider, where you can actually put the different amounts and for how long you would like to pay it back. And I created this last night just for the purpose of this presentation. So when I will say this interest rate there, just don't take them seriously. They are calculated by me being very tired at night. There's nothing related with the real interest, how they are currently in the market. So let's go on the topic. Here you have an amount. So I want to ask 2,000 euro and I want to pay back for 1 year. Then I was like, no, the interest rate, it's 2.42. Maybe I can explore another opportunity and say, like, I want more. I want 7,000 euros and pay it back in 1 year. And then I see there, okay, interest rate 1.71. Okay, what about 7,000 is too much? I get 5,000. And this, in the plot you show also there, you see a sequential data. And this is an example of sequential data. But people are different, and every individual has the right to explore their possibilities. And someone from here can go and say, like, you know, I don't want that much. I want, because I have a bigger problem, I want 50,000. Then I want to pay it back in 5 years, and I go and fill up those things. I get some results. Then I say, what about I try to get a bigger amount, 60,000, paid back in a longer term, and I keep on trying these kind of things to see if this actually fits my needs. I have created this way another sequential data. And this is something that is just a small part of the many sequential interactions you could capture from the web interaction. And this is just an example, and what we actually have, it's much more complicated than this, and in a bigger picture than what I showed here. So I said that different individuals have different needs. That means that this ranges when, for example, the amount of money we are requiring changes from one person to another, making also the range of these amounts different. How this change in direction can help us make some study, because sometimes you go ask more, sometimes you ask less, sometimes you change another feature, sometimes you try a new feature. Then you'd like to make some binning, you'd like to make some encoding, which it's actually going to capture these changes you are trying. And there are different ways, of course, to do that. And one of the ways I have tried here, it's the encoding strategy, which says, if at this point you go and fill up everything, and then in the next point, what you require, it's something larger than what you have previously required, then I am going to encode this as a +1 because it goes up compared to the previous one. In case it didn't change, it's 0. And in case you try something smaller than in the previous step, it's -1. And this is just like a technicality, but very important for the study we are performing here. To give an example, I am the person number 1, someone here is the person number 2, I go fill in some numbers, X, Y, Z, then everything in the first moment is filled in, it's changed, it's new information, so I have 1, 1, 1. In the second trial, I try something different, I change only X1, which is larger, and the remaining it's unchanged. This is why you have 1, 0, 0, and so on. So I think you can get the logic out of it, and then you also want to have a unique value for all of these changes. Okay. In our modeling strategy, it's essential to combine several well-understood features and put them into a complex model. And these features have the aim to explore the data as much as possible. We saw that using web-collected data, we can kind of have an encoding strategy to capture these changes. And we would like to obtain some information based on these changes, like how they are actually going up and down and how they are there in a sequence. In the case of the loan calculator, or also in general for financial fraud, the fraudulent class shows a different pattern from the legitimate clients. And then it's the moment to ask, can we actually use this kind of data to identify anomalies? The answer is yes. One of the methods here is anomaly detection by matching probabilities. The idea is that you model the non-fraudulent population and then measure how likely is that a new observation belongs to the normal population. Of course, you have to make some assumption, and the main assumption is that the fraudulent behavior is different from non-fraudulent behavior, and that the most legitimate application follow a similar path, and fraudulent application follow a different, more creative or anomalous, I would say, path. Then, in case this assumption are true, we can separate the two classes. We can separate the fraud from the non-fraud class. Okay, don't get scared. There's some math here, but it's fine. I will just explain you what it is. So one thing you have to remember, the Markov chain approximation, the first and the second formula, all it is saying that the future depends on the present. So what I'm going to take next, which step I'm going to take next, and in which direction depends on my present state right now. And the two formulas basically are just telling us and for the one who love math and like more formulas, this is just a way to calculate the probabilities. So how do you actually get these probabilities that given here, you are going here, or you are here, or you are going here, something like that. For example, which is the probability that I do not like chocolate? 0. Like if I put it this way, it's 0. But it's more to say, if you have like for the one who are more familiar with text processing, for example, if you have a big text and you say, which is the probability that I have this sentence, I do not like chocolate, and then you can decompose it based on the Markov chain approximation, and it's just like, which is the probability that I observe do after I, given I, times the probability that you'd observe not given do, and so on. So, easy, right? I hope so. Okay. To give an example, the weather. So suppose we have 3 states for the weather in Amsterdam. It's either sunny, it's either rainy, it's either cloudy. Then based on a set of observation, you kind of build some frequency, and then you measure some like how the weather changes, and then what you can calculate is, given that today it's sunny, which is the probability that tomorrow is going to be again sunny. If you live in Amsterdam, 0, Okay, I'm joking. It's just like always like to complain about the weather in Amsterdam. But okay, you get the point. Like, is the probability that if it's cloudy, which is the probability that tomorrow is going to rain, and of course it's high probability that it's going to rain and it's going to be sunny. Then you build a probability matrix, and in this matrix you have given the present state, which is the probability that you are in another state, and then you have all this number put up together. If we take 3 features, like 3 changes on the loan calculator, and then we said we have 3 ways of encoding these states. That makes 3 times 3 times 27 possible combination. So either I change everything, either I change 1, either I change 2 and then I leave 1 unchanged. Like all of this, it's 27 different states, and then the goal is to calculate this 27 by 27 probability matrix. And once you have this probability matrix, you basically done. You have all your works completed, and then you can use this to calculate all your probabilities for your population and assign that to the good behavior and to the bad behavior, try to distinguish them. Okay, I like to show this kind of a sunflower, because when you start with everything that has changed, you have 27 possibilities, and you can be in any of those. And taking the example I was showing before, if you have a person number 1 here, which has a sequence 1, 5, 10, 5, then the probability of this sequence for this particular person is decomposed based on the rule I was just explaining before, and you do that for every person on your population, and then what you end up is like something like that when you have the frequencies, and then you use that for calculating the probabilities, and that is basically building the Markov features. Okay, now it's time to go and see this. How do we actually do this exactly? Okay, so I have prepared for this talk a demo notebook. Here is, we are going to import all the features. Apart from the standard libraries that we use for modeling, I'm going also to use a function which is helping us to encode the states, and also a class called bgram model, which is going actually to make all the calculations under the hood for us, and then we will see the features. To start, we need a data set. And I think you understand I cannot show here bank data, but I can simulate data, and for that I used LSTMs to simulate the sequential data set. So I'm creating 10,000 entries, I'm creating 1,000 sequences, and I'm creating 3 features. Of course, we are going to drop NAS for just in this case, and then encode the states. And here you have how the data looks like. So you have a sequence, you have a class which I have assigned. Feature 1, V0, V1, V3, and then you see that for each of those features you have the encoded states and the changes the person has made. Actually, not the person, this is a simulated data set, but okay. And then you see the second, if you want to see this for the first class, then here it is shown here as an example. And if you want to see it for class 1, then it's also shown here in the other example how it looks like. So at this point, we are ready to calculate the Markov features, and then we are ready to call the class bgram, which I wrote to calculate, and then you just do the fit. It's motivated by scikit-learn, so I kind of follow always the fit method and stuff like that, because I think it's very friendly to be used by everyone. And now, after we have performed the fit, we want to see what is actually happening. So here it is in the print function. You have first data set, state, and frequency. You see that the state 0 has a frequency which is 1,143, and instead in the second data set, the state 0 has like much less frequency. So that is to say that the 2 classes are different, and the frequency of sequences is different, of course. Now, of course, it's also interesting to see and to visualize, and it's also a good practice to have these plots. And you like to see, okay, I want to see which is the most frequent B state, so which is the most change that happens there. And for that, there are for the two different data sets, which are different, of course, you plot the most frequent B states. In the first case, you see that a change from 26 to 0, it's much more frequent than other states. And if you look the first population compared to the second one, you see the difference, because the first one, it's 26.0, and the second one, it's 20.20. So if you like to change, of course, this is possible, and you just type 10 here, and you want to see let's say, the most 10 frequent, and there you go. If you want 20, you just put 20 there, and you have all your plots you like. Now let's move to the probability matrix. I suppose you are curious to see how does it look. Yeah, it looks like that. For model, the first model we have built here, I put like the option of log or true or false. Sometimes when you work with probabilities, they are very small, so you might prefer to go to the log space instead of non-log. So this is how the first population look like. This is the probability matrix for the second population. And you see something is going on there, because you have these two lines here, which actually show that something is going on. And what is that? Is that an anomaly? Can I actually detect that? What does it mean? So at this point, we think that we can distinguish the two classes, and we are ready to build the Markov features, which are shown here. So these are only few features that you can build. Then up to your case, up to whatever you want to do, you can add more and create more features. But you can take the mean of the sequences, you can take the minimum of the sequences, then you can normalize. Then if you want to go to the log space, you just go to the log space. And in this case, it's just the example is shown here. So it's the Markov sequence prob median, or the mean, and other features like that. After you create features, you also want to know, are they powerful? Can we actually separate them? And let's see in that case. So you want to see, and for that I have created the function predict proba, and that is going to give us for these two features how distinguishable are them. And here is the plot, and you can see, and for the ones who are familiar with modeling, when you put this in a machine learning model, definitely this feature is powerful. Definitely this feature is going to be predictive on your model, and this way you are going to be able to separate the two classes. A side note, I think we are all, maybe not all, but we know that missing values sometimes can be tricky to handle, and it's always based on the case you are working on, important to treat them properly. So in this case, I don't use one sequence length, I drop them from a model, but then there are some ways to treat because you have two populations, right? One population when you make the training, then one population when you're actually testing. And what you have an unseen state, which happening in the second population, which you haven't seen in the first one. And then you have to come up with some, depending on your problem, of course, coming up with some ideas how to treat them. Okay. Actually, I have lost track of the time. I don't know when I started anymore, but maybe I am over time or too early. Okay, well, maybe I'll get more questions because I think I was running, I was running fast. Okay. To conclude, Markov chain approximation, it's still a good approach for anomaly detection. And the positive sides, it's like you can understand and well explain what are these features doing. It is predictive when you have web collected data, and that's what I showed here. And you can perform behavioral studies on this kind of data and try to have in your model predictive features. And these features, together with other features, which I cannot share these details here, are used as a model we have in production, and it's very complex. And I think I arrived to the end. Thank you for your attention.